So up until now in this particular unit, aside from angular variable stuff, when we're talking torque, we've been talking about torques that balance. And so talking about systems in rotational equilibrium, right? Now, if you remember years ago, when you first learned about Newton's first and second laws of motion, we learned that if an object, in middle school you learned an object at rest stays at rest, an object in motion stays in motion. And then you grow up and you're like kind of adults and you're like, oh, an object with a net force of 0 on it will not accelerate, i.e. an object at rest will remain at rest unless a net external force acts on the object. Same thing, an object moving in a straight line will continue moving in a straight line unless it feels a net external force. And so really what that says is that Newton's first law, which mathematically we can express like this, for translational motion, the net force is 0. If the net force is 0, then we know that the object is in translational equilibrium. And then we move on to Newton's second law, which says that the net force is equal to mass times acceleration. And then we learn that Newton's first law is simply a special case of the second law. The second law states that the acceleration of an object directly proportional to the net force, inversely proportional to the object's mass. And then Newton's first law is just a special case. When the acceleration is 0, the right side becomes 0, therefore the net force becomes 0. And you can interpret that as the net force being 0. When the net force is 0, the acceleration is 0. If the acceleration of an object is 0, then if it's at rest, it stays at rest. If it's moving in a straight line, it continues moving in a straight line at constant speed. So Newton's first, second law is essentially the same. Newton's first law, though, is just the special case where the acceleration is 0, and the net force must therefore balance out. Torques work the same way. Last week we talked about how we use the rotational equivalent of Newton's second law to define the concept of rotational inertia. And to do so, we said that the net torque is equal to the rotational equivalent of mass, which is either called the moment of inertia or the rotational inertia, times the angular velocity. But then we talked about equilibrium situations, not translational equilibrium, but rotational equilibrium. And if we're in rotational equilibrium, we're either at rest or we're spinning at a constant angular velocity. In either case, the angular acceleration is 0. So the right side of this equation is 0, which implies that the net torque must also be 0. It doesn't imply there's no torque. It just implies that any torque is being offset by an equal torque in the other direction. But remember, other direction means in the other rotational direction, right? They can both be pointing down, but they can be in the opposite direction when it comes to the torques that they create. Okay. And if you remember, before we did the equilibrium stuff, we defined the rotational inertia as the resistance that an object has to angular acceleration. Remember, the mass of an object is just a measure of its inertia, which is a resistance to a change in motion or an acceleration. The larger the object is, the harder you got to push it to give it the same acceleration. Same thing applies to rotation, right? The larger the rotational inertia, the harder it is to get it spinning. The harder it is to stop it from spinning. And then we talked about how the rotational inertia for a point mass was, and this is why I taught Newton's second law first, so we can talk about what the rotational inertia for a point mass would be. It's just the mass of the object times its distance from the axis of rotation. Remember, we talked about a point mass that's on the end of a string going around a circle, but then that distance gets squared. Okay. And we use this in conjunction with Newton's second law for translational motion to define this quantity here. And then I told you about, we're not going to do it in this class, but you will next year when you take AP Physics C, which I'm sure all of you are. Well, not all of you. But then I told you that you can then use this general equation to determine the rotational inertia of what we call extended objects, like this uniform disk, right? So it's uniform density. What I can do mathematically is take this disk and break it up into a bunch of little tiny point masses. Each point mass, each little piece of mass here, has a mass m and a distance from the center of the disk. And then if I do that an infinite number of times with all the infinitesimally small point masses and add up all their individual rotational inertias for a disk slash cylinder, because a cylinder is the same thing as a disk is just a flat cylinder, but they're all cylinders, we see that the rotational inertia of a cylinder has an equation. It is 1/2 times the mass of the whole cylinder, not a point mass of the whole cylinder, times the radius of the cylinder squared. All rotational inertias will have an m and an r squared in them. So, or a mass and a length squared. Okay. And it's interesting because it doesn't seem like this would happen, but the technique that we use to generate these equations using calculus, the same technique, not the same, but a very similar technique that we use to determine, say, the electric fields generated by charged objects, or the electric potential, otherwise known as voltage, due to a charged object, like a capacitor plate or a battery terminal or something like that. Not really a battery, that's more chemistry. Talk to Mr. Kelly about batteries. But it's a very ubiquitous technique that we introduce in AP Physics C or any introductory calculus-based physics course to determine what the rotational inertia of an extended object is based on the rotational inertia of a single point mass. It's a very important technique. It's one of the first really highbrow, really higher level techniques that you learn how to do physics at a higher level. Okay. So, just some basics here, but now I want to focus on rotational inertia by itself. Rotational inertia. And I'm going to write the definition up here because it's important. It is the resistance of an object, and I'm going to say an extended object. So we're not talking about point masses. An extended object is literally not a point mass. It could be a hoop like this. It could be a disc like this. It could be a long solid rod like this. So an extended object. It's the resistance of an extended object to angular acceleration. Just like inertia is the resistance of an object to translational acceleration. Okay. Now what makes rotational inertia more complicated, and it's already more complicated, Newton's second law for rotation, because net torque is more complicated than net force. Net force is a single push or a pull, right? It's a single interaction between objects that results in a push or a pull on an object. Some kind of change in translational motion. Torque is a relationship between three separate quantities, right? Force is just like technically one quantity. Torque is due to the force, just like force is, but it's also due to where the force is applied on the object, right? Which dictates where the lever arm is. And it's also due to the angle that that force makes with the lever arm. So torque is due to three separate quantities. So already Newton's second law for rotation is more complex because of that. But then we have the fact that rotational inertia is also more complicated than mass because it's due to two factors as well and the geometry of the object. Okay. So, and I pointed this out when I introduced the concept, but if you have like a rod like this, it's not that heavy, it's a couple pounds, but it's intuitively, we know it's much easier to rotate it like this than it is to rotate it like this, right? But the mass has not changed, right? The mass has not changed yet. Its rotational inertia definitely has changed. You can feel that change, right? So what happens is that while the mass of the rod hasn't changed, the distribution of that mass has changed. And so when you're talking about rotational inertia, the R's or the L's, you want to have it in your head that they're really talking about how the mass is distributed about the axis of rotation. Right? If I have this axis of rotation here, I got this much mass. The farthest away the mass gets is L over 2. The farthest away mass gets over here is L over 2. If I go like this, now from here out, that's farther than L over 2. Right? It's farther away. Mass hasn't changed, but because I've taken some of the mass and increased the R values for some of the mass, the overall rotational inertia of the object increases. And it increases quite a bit. It turns out that the distribution of the mass is much more important when it comes to angular or rotational inertia than it is the mass itself, because it gets squared, right? When something gets squared, when you change it, it has a bigger effect than if you don't square it. Make sense?
The R value is just the lever arm, yeah?
Yeah. But you don't have to have a torque in order to have rotational inertia. So it's very often the lever arm, but really it's just the distance from the axis of rotation to the mass involved. But to have a lever arm, you literally have to have a torque, which means you need to have a force. But this guy, if he's floating out in space, there's no torque on it, but it still has rotational inertia.
Right.
That's a good question. When you're just talking about rotational inertia, think of R as just where the mass is located relative to the axis of rotation. When you're talking lever arms, it's where the force is actually acting on the object. Very often they're the same. More often than not, they're the same. Okay. All right. So again, it's the distribution that's actually more important. The distribution of the mass is actually more important than the mass itself. Again, because it gets squared. Now, this is a very, very famous demonstration. I got 3 objects here. I got a disk, a uniform disk, so it's uniform density. And then I have, not a disk, obviously, it's a hoop with a rod going through the center. And then I got a hoop with nothing in the center. All 3 of these are the same mass. They're manufactured to be the same mass. And if I let them roll down the ramp, first of all, if I let them roll down the ramp and there's no friction, 0 friction, what happens to this disk as it moves down the ramp? It wouldn't roll. It would just slide like this. If there's literally no friction here, it would just slide. And since these 3 objects have the same mass, they're just going to slide down at the same rate. Right? If you do the free body diagram for all 3 of these guys, free body diagram is exactly the same if there's no friction. If the free body diagram is the same, then the resulting acceleration that you would measure would be the same. Okay? Whose phone is that? Is that you, Kurt? Unbelievable. So, but the thing is, they're not going to roll down at the same rate. They're not going to, keyword, roll. They're not going to roll down at the same rate. Okay? They would slide down at the same rate because they would have the same free body diagram. The Newton's laws for translational motion would be exactly the same for all 3. But yeah, when you actually talk about the rotation, we got to be more careful. And so first of all, when this disk rolls down, let's say the disk, still on camera, right? Not on camera. Dang it. Sorry, everyone at home. Here, now you can see what I'm talking about. This disk right here, when it rolls down, what's its angular velocity to start with? 0. Is it 0 now? No. So its angular velocity increased. Therefore, it has an angular acceleration. Therefore, what can we say about the net torque? It just can't be 0, right? It increased from 0, yeah. Right? If the net torque is 0, then it doesn't rotate. If it doesn't start while rotating. So there has to be a net torque. Anytime you roll something downhill, there's a net torque that's causing the angular velocity to increase. When you roll down it, yes. What force is creating the torque? What?
Friction, yeah. It's gravity and friction.
Is that friction? Did you say friction? Yeah. It's friction. Now, it's not going to happen without gravity. You do your free body diagram, there's a component of gravity that wants to pull the center of mass of the object down. But since it's pulling it down, you have friction that's acting here, not at the center. Remember, gravity doesn't create torque on an object.
There was no friction, it just allowed.
Yeah, exactly. But since there's friction, there's a force that points up this way at a distance away from the axis of rotation that actually causes the angular acceleration. And so that's why objects roll when they go downhill. So if I let all 3 of these guys roll at the same time, but they are going to roll, they're going to have the same torque, right? They have the same normal force because they have the same mass, you have the same normal force, so they have the same friction force. But that means that whichever object has the smaller rotational inertia will have the larger angular acceleration and will therefore roll down faster. Okay. So based on all this, which object do you think is going to roll down the fastest? Again, which object rolls down the fastest will correspond to which object has the smallest rotational inertia. And we know that rotational inertia is due to the distribution of the mass, i.e. the farther away the mass is from the center, the axis of rotation, the more rotational inertia it will have. So which one do you think gets down the hill faster? These are all the same mass total. Yes, sir.
Wouldn't it be the one that just has nothing in it? It's the third one.
This one?
Yeah.
Do we have some votes for that one? Does anyone vote for this one?
No, that's not gonna be right.
Does anyone vote for this one? Joshua? Remember I said fastest. Which one gets down the hill fastest? Meaning which one has the smallest rotational inertia?
Yeah, so it would be the black one, right?
So it'd be the black one? So you're changing your vote?
I didn't vote.
Oh, okay.
But I didn't vote.
So you say that one?
Wait, so
The smaller the rotational
Think about it.
inertia, the faster it'll go down.
Yes.
And
The smaller the rotational inertia, the bigger its angular acceleration will be, meaning the faster it'll be rolling.
Actually, the black.
It'll be the black one. That's what Kirk says. Anyone want to change their mind from this one?
R is the distance from the center of mass to the place of
So the larger
To the place where the mass is actually
so
located.
the larger the mass is, the larger the rotational inertia. So the farther away.
They're all the same mass.
So then the farther away from the center. the lower
Yeah,
rotation.
yeah.
That's all.
So let's just see. And then we'll explain afterwards. Which one made it down first?
Black one.
The disc, right? The uniform disc.
What if it's the middle one? There's no way that it's in the middle.
You'll be in the middle, right? Exactly in the middle. So the reason, and usually it's about half and half. Half people will say this one, half will say that one, and no one says that one. The reason, these are the same mass, but there's a lot of mass, a lot of little pieces of mass that are close to the center, meaning they have small values for R. So the total rotational inertia for this guy is going to be smaller because all of the mass in this guy has large values for R. All of the little pieces of mass. Far away. Remember, the farther away from the axis of rotation you have the mass located, the higher the rotational inertia is, the harder it is to get it to rotate. So the closer the mass is to the center of mass, not all of it, right? We're talking big kid physics here. We're not talking like a single thing located here. We're talking about the distribution of the total mass. A lot of that mass is congregated towards the center here, where none of it is here. So all of the mass here has large values of R.
Does
Okay.
that mean that the hollow one would be harder to stop?
Yeah. Yep. Larger rotation, and we'll talk about that in a little bit.
what if the friction was different? Like, what if one of them had a rough surface area, or like a rough surface area? One of the
Well,
other?
You have two different variables, and that's not a science.
Yeah, and yes, these are slightly different surfaces. However, it's static friction, and the static friction is the one that's going to vary, and so they're going to be really close. They're going to be really close to each other. That is a good question. Making sense? And the reason that this guy is in the middle is because most of its mass is congregated to the outside, but it's still got some towards the center, and so that'll reduce the rotational inertia a little bit from where it would be here. Okay. Make sense?
Yep.
All right. Just to drive this point home, I thought I was on camera for all that. I'm sorry, guys at home. I'm making two versions. Well, I think this is already the better one. Okay. Just to drive this point home, and to relate it to our motion graphs, which I'm sure we all remember with amazing clarity. Here I got an object that's going to rotate. Clear out the space a little bit. So I got this object. First of all, what's the net force? These thrusters create the same force. What's the net force on this object? Zero. So it's not going to translationally accelerate, obviously. Okay. If they were both pointing in the same direction,
There would be no rotation.
there'd be no rotation, there'd be no net torque, but we'd most definitely have translational acceleration. But since they're pointing in opposite directions, the net force is zero. However, they both want to cause counterclockwise torque. And so in this case, we definitely would have an angular acceleration. I'm plotting here angular velocity versus time. So the slope of that is our angular acceleration. The slope doesn't change, therefore the angular acceleration does not change. Now I'm going to take this object, and you all won't be able to see this, but the mass of the object is 20 kilograms. So what I'm going to do is increase the size of this object, and then it increases the masses automatically, but I'm going to change it back to 20 kilograms. So now I got an object that's 20 kilograms, same mass. I haven't changed the location of the thrusters, therefore the lever arms for the thrusters have not changed. The angle is 90 degrees, right? Lever arm, and then thrust force, 90-degree angle. So the torques have not changed. The mass of the object has not changed. However, I've increased the distribution of some of the mass. I've taken some of the mass from the middle and sequestered it farther away from the axis of rotation. So in response to those same exact torques, I get a smaller angular acceleration. Even though the mass is the same, even though the net torques are the same, the only thing that I've changed here is the distribution of that mass, thereby changing the rotational inertia of the object. Okay? I've increased it because I've increased values for R. So increasing the rotational inertia decreases the resulting angular acceleration, which is literally what we see right there.
So how do you find the value for R in that case?
Again, that's a calculus-based physics. R itself, when you see that, like the rotational inertia for a cylinder, R is literally the radius of the cylinder. M is literally the total mass of the cylinder. To arrive at that involves mathematics that you know, but that we don't do in this class.
Right. So.
And we're not going to go over it because we don't have time for it.
Right, but in a physics 1 class, will they give you the value of R and then say solve for inertia?
If they say you have a disk, generally what they do, they either give you the numerical value, because right, you can boil this down to a numerical value. 1/2 mr squared, but if you know m, you know r, you just plug those in and you get the numerical value. So they'll either give you a numerical value for the rotational inertia, ask you to calculate the the value of the rotational inertia, or they'll give you the expression. Like you don't have to remember the expressions at all.
Right, but I'm saying like, will they give you the number value of R if they ask you to solve for rotational inertia?
I mean, I haven't seen that very often, but you could. They could say, the pulley's mass is 10 kilograms. It's got a radius of 3 meters. What's its rotational inertia? I mean, it's probably more basic than any AP Physics 1 question would be. All right, we good? All right, let's revisit something that we did years ago. Years and years and years ago.
We've been here years,
Yeah, feels like it.
doesn't it?
It's just because you're my favorite class.
I know, we just love spending time with us.
So we're not going to do this one, but you guys remember Atwood machines?
Those are the machines that.
It's just that. That's what they use to relate, weight forces and accelerations and stuff. Modified Atwood machine we saw. Usually we do a lab, but because it's COVID year, we didn't do a lab. We might have done a virtual lab. I actually don't remember because that was, like I said, years ago. But we had this situation going on. I got a hanging mass, which I'll call MH. And I got this mass here, I'll call mass of the cart because it's going to be this lab setup up here. And when we did this, we made some assumptions. We assumed, first of all, no friction. No friction between the cart mass, no internal friction in the pulley. I got a pulley here, you can hear the friction. Right, and it stopped already. So there's friction now. We are going to still assume that. Okay? But we also assume something else. What else do we assume? You guys remember? It's about the pulley. Ideal pulley. We assumed an ideal pulley. Good job. And again, an ideal pulley is massless and frictionless. Now, objects cannot be massless unless you're a photon or a graviton or one of those weird particles. But extended objects cannot be massless. Okay. But it was this assumption that led us to make a valid statement. If a pulley was massless or frictionless, what could we say about the tensions in either side of the string, or in the string on either side of the pulley?
They were proportional, or the exact same.
They were exactly the same. Tensions are the same. If we have an ideal pulley, then either side, the tension on either side is the same. And I just told you to know that. Now we can actually understand why that is. Because if I have tensions on both sides, they're going to exert forces on the pulley. I'm going to have a tension pointing down, and I'm going to have a tension pointing this way. Now I know that those tensions create torques on the pulley, right? Yes, I have two other forces. I'm not going to label them now, though, because I don't want to clutter the diagram. I have a weight force that's drawn from the center of mass. There's also a normal force from the axle on the pulley, which generally kind of points up this way a little bit, which we'll talk about later, but not right now. But I don't need to worry about those two forces because they act on the center of mass of the object. Therefore, they create no torque. They create no torque. Do these two forces create torques?
Yes.
Yeah. And both of those forces have the same lever arm, R. Both forces, and again, I said this before, like if you have a pulley, a string wrapped around a pulley, show me a way that you can pull on that pulley where the string doesn't make a 90-degree angle with the radius, right? It's impossible. Unless you like push it down, then you can do that, right? But then if I take my finger off, then it immediately goes to 90-degree angle. Now we can say it makes a 90-degree angle to the lever arm, right, of the torque. So that's what's nice about pulleys with strings wrapped around them and stuff, is that the lever arm is always going to be 90 degrees to the tension force, so the sine of the angle between the two will always be 1. So that simplifies our lives a little bit. But if the pulley is not massless and frictionless, i.e. if it's not an ideal pulley, will this pulley rotate in response to these two forces, which we have assumed up until this point are exactly the same? Yeah. You need a non-zero net torque to get it to rotate, right? Obviously, whenever I let this guy go, pulley's rotating. It wasn't rotating at the start. Oh, man, yeah. Let me do that again for the folks at home. Calm down, Kurt. Stop kicking my stuff. So I got a pulley, I got a cart, I got a modified Atwood machine, and when I let it go, pulley's not rotating, pulley started rotating. So these two tension forces literally cannot physically be the same. Now, if the pulley was massless, then yeah, it can accelerate without a tension force, right? Without a net force. If the pulley, if it was massless and frictionless, it can accelerate with that. Or you could just say, well, if it's frictionless, it doesn't even need to spin, right? And the string can just slide over the top, right? And it would behave like an ideal pulley. So in reality, though, no pulley is ideal. In reality, pulleys get close to being ideal, like this guy. This guy you can barely hear when it's spinning. And it's got spokes cut into it, and it's very thin. And the spokes remove even more material, so it's very low mass. So for practical purposes, we can assume this is an ideal pulley, even though it's not. Just like in chemistry, you assume gases are ideal, even though they're not 100% ideal. But they behave like it so closely that you kind of can. But in reality, like if you're going to be an engineer that's going to, design the cranes that you use to build skyscrapers and stuff. Sorry, I can't do more than one thing at a time. Then you guys seen that? I brought it up before. When you build a skyscraper, I used to wonder about that when I was a kid. How do they build things so tall?
I asked that question.
Well, the crane goes up with them, right?
Yeah.
The crane goes up with the skyscraper as it gets built. But that crane needs to be able to pick up stuff that's from the ground, like those big I-beams that are several tons apiece. And so they pick those up with steel cables that are looped over very large pulleys. And a lot of those pulleys are so heavy you couldn't lift them up. They're so heavy. And so their rotational inertia is most definitely not even close to being ideal. And so if you're designing those cranes, you got to be on top of it. You got to incorporate that physics into your design. What's up?
You can't assume that one's an ideal.
No, definitely not. And you don't want to mess up one of those cranes, because when those cranes come down, and it has happened a few times, a handful of times in history, and it's bad. It's bad. A lot of people get hurt. And especially imagine it's up on the 50th story, giant crane, and then it falls in a big city. Bad things can happen. If you're the engineer that designs that and that happens, then you can get in trouble, actually. You can actually go to prison because you've signed off on it. So, if you're going to end up doing that, make sure you're incorporating the pulleys into your design. Okay? All right. So let's say that we have a problem. Oh, wait, why did I do that? Why did I do that? Okay, let me draw that again. So I got two tensions. Let's say that in reality, this pulley is going to rotate that way, just like it did when I ran the experiment just now. Well, that would imply that this tension force needs to be larger than that tension force, correct?
Yeah.
So those two different tensions, so I might call that FT2 and this FT1. Okay, two different tension forces. You need a difference in tension forces in this case because you need a non-zero net torque to get the pulley to actually rotate. Okay. Same lever arms, right? Same 90-degree angles. Okay. So all that being said, let's say that we are tasked with doing this on a free response question. Say we are told to determine the experimentally determine the numerical value for the pulley's rotational inertia. Okay. And I'm just going to list what I measured. I made some measurements at the beginning. These kind of problems typically say what quantities would you have to measure? What tools would you use to measure them? Well, I use my scale over there to measure the mass of the cart. It's 0.4901 kilograms, or 490.1 grams. The hanger mass was 0.0498 kilograms. And the radius of the pulley, and we'll put a little star there because we're going to have to talk a little bit more in detail about that, 1.8 centimeters or 0.018 meters. Those are the things I measured initially. Now I put a star on the pulley here. Well, the pulley actually looks more like this. There's if you look at it right now, that white pulley looks like that, but there's a groove cut into it kind of deep. And that's where the actual strings are attached. That's where the string loops over. Okay. It's got a groove to keep the string in there, obviously. So, yes, we know the equation for the rotational inertia of a uniform disk is 1/2 mr squared. Or if you don't remember that, it's in the table in your notes. If you need it for a test question, it'll be given in the test question. This is not a uniform pulley, though. It's been grooved, and so it's not as simple as that. So usually for an irregular object, you actually experimentally determine the rotational inertia of it by exerting net torques on it that are measurable or calculatable, and then measuring the resulting acceleration and then backtracking and kind of deconstructing it in order to determine the rotational inertia. Okay. So when I say the radius of the pulley, really I'm talking about that distance. Okay. So the lever arms for those forces aren't going to be the radius of the pulley as you see it here. It's going to be that distance itself. And to measure that, all I did was measure the radius of the pulley. And then I took my ruler and I stuck it down in the groove, measured that distance, subtracted it. That's how I got the actual, the radii that will be the lever arms for the tension forces. Okay. All right. Now, one of the things that you can do with with an Atwood machine where you assume ideal pulleys is, because these tensions are the same, very often the question says determine the acceleration that the system will experience. You know that both of the objects have the same acceleration. You know that the tensions are the same. So the tension would be an unknown. The acceleration would be an unknown. So you would have two free body diagrams that you could draw, two equations that you can get, equations of motion using Newton's second law. And then so you can determine the tension and the acceleration because you'd have two unknowns and two equations. Now, though, we don't have the same tension on either side, so that same question would require you to solve for three unknowns. You'd have the acceleration, you'd have this tension and that tension, which means just a free body diagram for these two wouldn't be enough. You'd have to generate a third equation, but since we now can do Newton's second law for rotational motion of the pulley, we can now generate that third equation. Okay. This question isn't asking you to do that, though. This question is asking to determine the numerical value for the pulley's rotational inertia. The acceleration, we're actually going to measure. We're going to use Logger Pro to measure. I got the motion detector here. It's already set up. So we can actually measure that. So with a modified Atwood machine like this, or real Atwood machine, which you'll see on the Quest assignment, and we'll use kind of one for an example problem tomorrow, at the start of tomorrow, we can now generate three equations. We can use Newton's laws for translational motion to talk about the translational motions of the two masses and generate equations of motion for them. And then we can talk about the rotational motion of the pulley with Newton's second law for rotational motion and generate a third equation that way. All right, so all that being said, let's go ahead and draw our free body diagrams. Let's do the cart first. So the free body diagram for the cart. And I'm going to assume to the right for the cart is the positive x direction, and to the up is the positive y direction. So what forces are acting on the cart? We are going to assume no friction now. So let's circle that. But we are now not going to have an ideal pulley. The tensions are not going to be the same. So what forces are acting on the cart? Force of gravity, MCG. Force normal. And tension force. And we'll call that, I think I call that tension 1. We call that tension force 1. And is the object accelerating in the y direction?
No.
No. Okay, it would be weird if it was. So it's not accelerating in the y direction, so we just need to talk about the net force in the x direction. And by Newton's second law, we know that the net force in the x direction is the mass of the cart times the acceleration of the cart. Net force in the x direction, I only got one of them. Tension force 1 is going to be equal to mass of the cart times the resulting acceleration. There's an equation with one of my unknowns. Again, the acceleration sometimes is an unknown. In this case, we're actually going to experimentally determine that so we can get a numerical value for the rotational inertia of the pulley. All right, let's move on to the hanging mass. What forces are, I'm going to put it up a little bit so I can save some room. What forces are acting on the hanging mass?
Force of gravity.
Force of gravity,
Force of tension.
force of tension. So hanging mass, weight force. Is the tension acting on the hanging mass the same, or, well, it's not the same obviously, is it bigger or smaller than the first tension force?
Bigger.
It's bigger, nice. It has to be, remember the tension force that's pulling down on the pulley is the same as the tension force that's pulling up on the hanging mass. As long as the string is lightweight and its weight force doesn't matter much at all. The tension force that's acting this way on the pulley is the same as Newton's third law, same as the tension force that's pulling to the right on the cart. So because the pulley we know is going to rotate this way, the downward tension force has to be larger than the leftward tension force. So I'm going to draw my tension force 2 to be larger than the tension force 1 that's acting on the cart. Now this equation is a little more complicated, and so is the coordinate system, but remember years ago when we learned when you have a pulley, it kind of redirects the coordinate axes. And so if we call to the right the positive x direction for the cart, down for the hanging mass, I know it's weird because it's pointing down, that's the same direction, right? If the cart's moving this way, the hanging mass is moving downward at the same rate. So we can kind of lump them together. In that case, and obviously there's no forces horizontally on this guy, so we don't need to worry about those. probably going to have to finish it up tomorrow. Okay, and so the equation of motion for this guy, the net force, I might leave off the x just so I don't confuse anyone, but the net force we're talking about is the up and down motion. Down I am going to call the positive direction because that's the direction it's actually moving. So the net force on the hanger is going to be mh times the resulting acceleration. But more than one force. Here I only have one force acting as the net force. Here I got two of them. And I'm going to call the weight force the positive one, so mhg minus that tension force, T2 equals the hanging mass times the acceleration. Remember though, these two accelerations are the same. And for reasons you'll see in a minute, I'm going to solve this equation for the tension force. Hopefully this is not too much of a... I'm going to skip some steps. I'm going to add this guy to that side and subtract that guy from that side. And I get at the tension force, I can actually factor out the mass hanger. I end up with this. If I solve this equation for the tension force too, I get that equation. And I'll show you why I did that now. So those are the two equations that up until now we could already solve for. We just assumed those tension forces were the same, so we can then combine those equations. But now that we know that those tension forces are not the same, if we didn't know them and we don't know the acceleration, that's three unknowns or just two equations. Not good enough. So now we got to take a look at the pulley. And when we're looking at that pulley, if the tension force pulling up on the hanger, then it has to be pulling down on the pulley with the same force, so Ft2. And if the tension force is pulling to the right on the cart, then that tension force needs to be acting backwards at with the same force on the pulley. Again, that's consequences of Newton's third law. Oh, and I didn't draw it in the right spot. Sure. That's tension force. What? I can draw the lever arms in here. They are both the same. And they are both this value, that value that I measured. And the angle between those lever arms and the tension forces are the same. Are 90 degrees, sorry. So the sine of those angles will both be 1. And now I can use Newton's second law for rotation. Net torque equals rotational inertia times angular acceleration. And this is also the first time that I will use a non-standard coordinate or non-convention coordinate system for my rotating object. Because I know this object is going to rotate clockwise, I'm going to define clockwise rotation as the positive direction now. Remember, any coordinate system, you're free to choose whatever coordinate system you have.
So
Like,
Ft1's negative?
what's that?
Ft1's negative?
Ft1, the torque from Ft1 would be negative, yeah. So I'm going to call this my positive rotation direction, so positive angular velocity direction, positive angular acceleration direction. So in that case, my net torque, I'll have a positive torque from Ft2, from tension 2. That torque is force times lever arm, which is just R, radius of the pulley. That effective radius of the pulley times the sine of the angle, which is just 1. So that's the positive torque. I got the negative torque from the other tension, Ft1, times that same R value, times the sine of 90, which is 1. That's going to equal the rotational inertia, I, which is really what we're asked to find here. We want to find the rotational inertia. But alpha there is technically another unknown. It's technically a fourth unknown. And this is the trick that you have to use to bypass that, to end up expressing that in terms of another known quantity. We know that the cart is accelerating this way. We know that the hanging mass is accelerating downward with the same acceleration. Therefore, this point on the string has to be accelerating this way at that same acceleration. Therefore, a point on the string that's lying on the rim has to be accelerating with that same linear acceleration, which means any point that is equidistant on that rim from the axis of rotation has the same acceleration. And we know how to relate the angular acceleration or angular velocity or angular displacement of a point on a rotating object to the linear variables, the corresponding linear variables, using equations such as the linear acceleration of the string as it's on the pulley, or any point that's on that pulley at that distance, is equal to the radius times the angular And then I can solve this for alpha to have an expression I can plug in involving my known values, the acceleration and the radius of the pulley. So I can substitute that in right here. Okay. And so there's our third equation. Right, now I got 3 equations. And as long as I experimentally run my experiment, as long as I run my experiment and experimentally determine the acceleration, which is in all 3 of the equations, the only 3 unknowns would be what I'm looking for, the rotational inertia, and the 2 tensions. Okay, and the easiest way of solving this system of equations for I would just be to solve this for the tension force 1, which we already did, plug that in for the tension force 1 here, solve this equation for tension force 2, which I already did, plug that in here, and then the only unknown would be the rotational inertia. So tomorrow at the beginning of class, we'll actually run this experiment, measure the acceleration, and finish that off, measure the rotational inertia of this pulley. It's kind of a small pulley. It's pretty lightweight. There's some friction there, but I'm assuming it's not going to be a large value, but we'll wait and let the math tell us. That's it.